Hi everyone. Uh, Now that we have finished our discussions on instrumentation amplifiers, I thought I'll discuss a few problems on instrumentation amplifiers, uh, something that's based on what we discussed so far. So shown here is an instrumentation amplifier with a second stage gain of 1. If you see, the resistors here are R and this is also R and R. So the second stage subtractors gain is just 1. The first stage gain is actually 1000 because the resistance RF is given to be 499.5 times R. So that is the first stage gain. If you want to write, it will be 1 plus 2 RF by R, which is 499.5 times 2, which will be 999 plus 1, which will be 1000. It's given that the UGB of these op amps that are used in this instrumentation amplifier are not ideal, and the UGB of the op amps are given to be 100 megahertz. What we are supposed to find is that if a differential input of 1 millivolt is applied at the input, a differential step input of 1 millivolt is applied at the instrumentation amplifier's input, what will be the settling time, 5 time constant settling time at the output of the instrumentation amplifier. So it's a problem based on frequency response. We are supposed to find out what is the overall time constant of this instrumentation amplifier. So since we know the gain, the first stage gain is 1000, I just wrote it here, 1 plus 2 RF by R1 is 1000. G2 is R4 by R3. In this case, R4 and R3 are same. So R4 and R3 are same. So it's just 1. And whenever we are doing settling time, which means we need to know its frequency response. So if you are asked to find the settling time, we know how to find settling time based on frequency response, right? So once you know the frequency response based on the pole, for a single pole system, time constant of the system will just be inverse of the pole. And for a two pole system, it will be slightly more complicated. We can't define time constant, but we can define settling times. Okay, so we'll see what kind of a frequency response does this instrumentation amplifier have. Now when we want to derive frequency response, recall we said that the instrumentation amplifier can be seen as a two-stage amplifier. The first stage frequency response is given by G1 times 1 plus S by omega 1. The first stage 3 dB bandwidth, if we call it omega 1, or the first stage closed loop pole as omega 1. And the second stage again can be written as a DC gain and a single pole system with a frequency omega 2. And what is the value of omega 1? Here I am calling it as F1. Omega 1 means the units are in radians per second. F1 means it's just units in hertz. So omega 1 is 2 pi F1. So that's the relation we are using here. So therefore F1 is Fu times beta 1. Remember omega, the UGB of your first stage, the 3 dB bandwidth of the first stage is simply given by beta, the feedback factor of the first stage times, which we are calling beta 1, times omega u. So I'll write this as Fu. F1, this is just in hertz units, it's just the same thing, and will simply be equal to Fu times beta 1 or Fu divided by 1000 with the gain of the first stage. So since Fu is given to be 100 megahertz, you divide it by 1000, you should get 100 kilohertz. So that's the 3 dB bandwidth of the first stage. The second stage, the gain is just 1, G2 is exactly equal to 1, and the feedback factor, if you see, the feedback factor for this stage is just half, right? The quantity that is returned back is just first stage, if it is being driven by the output of an op amp, so we can assume the small signal output impedance here will be 0. So the feedback factor will be R by R plus R, which is 1/2. So the UGB of the second stage, omega 2, is omega 2 times beta, which will be omega u times beta, which is omega u by 1 plus G2, right? G2 is 1, so it will be half, omega u by half. So F2, the 3 dB bandwidth of the second stage, or the pole frequency of the closed loop pole frequency of the second stage, is given by Fu by 2. Since Fu is 100 megahertz, I'm sorry, I think this is 100 megahertz, divided by 2 is 50 megahertz. So this is 50 megahertz. So now if you plot it on the frequency response graph, so this term is going to be at 50 megahertz. In fact, this plot is not shown to scale, but you can now see that for from 100 kilohertz to 50 megahertz, that's like more than 2 orders of magnitude. 1 order of magnitude from 1 kilohertz, 100 kilohertz, you will go at 1 meg. Another decade you move away from it, you go to 10 meg. So it's more than 2 decades away. Since it's more than 2 decades away, for all practical purposes, we can treat it like a single pole system. Okay, the settling response will be very close to single pole because the first pole frequency is much lower than the second pole frequency. So the overall 3 dB bandwidth, is approximately equal to F1. If you guys recall the results from the previous lectures on the frequency response of instrumentation amplifiers, we argued that the 3 dB bandwidth will always be lower than the lowest of the 3 dB bandwidths of the 2 stages. In this case, F1 is almost 2 orders of magnitude lower, more than 2 orders of magnitude lower. So we can easily assume that the 3 dB bandwidth will be very close to F1 itself. So then the time constant is simply given by 1 by 2 pi F1, which is simply 1.6 microseconds. So the settling time is roughly 5 time constants, which is 8 microseconds. So that is, if I apply a step input of differential step input of 1 millivolt, this is 1 millivolt step, the output will be 1 millivolt times the DC gain, which is 1000. It will be 1 volt. That's the steady state output voltage. It will reach the steady state output voltage asymptotically with a time constant of 1.6 microseconds. So this should be 1.6 microseconds, and it will reach the steady state value with more than 99% accuracy. I think it's 99.5 or something. Within 5 time constants. Okay, I think it's 99. So with 5 time constants. Okay, that will be 8 microseconds. That's the overall settling time. Okay, so that's one problem on frequency response of instrumentation amplifiers. The other question is a little bit interesting one, something that for you guys to think about, because I just very briefly introduced about noise. Okay, so now you are supposed to find out, it's the same instrumentation amplifier with the same gain of the first stage is 1000, the gain of the second stage is 1. We are supposed to find out what is the noise contributions due to the 3 op-amps. You have 3 op-amps in the circuit. All the 3 op-amps have input referred noise. Let's assume the input referred noise voltage as Vn. Assume that for all the op-amps it's the same. It's Vn here, Vn here, and Vn here. Then what is the overall input referred noise of the, I'm interested in finding out, let me pose the question this way. Let the integrated noise, if I integrate it over a certain band of frequencies, is given to be, or let me, instead of integrating noise, let me say that what is the input referred noise floor? Input referred noise floor, if it is given that the noise floor of a single op-amp is 1 nanovolt per root hertz. So what did you do? You designed the op-amp, measured its input referred noise voltage, and it turned out the noise floor, the thermal noise floor of the input referred noise floor of the op-amp turns out to be 1 nanovolt per root hertz. You are supposed to find out for the entire differential instrumentation amplifier what is the input referred noise due to these 3 op-amps. And then we have to see which one contributes the most. So to find the input referred noise, again we can apply the principle of superposition. We can assume other 2 noises are 0. So remember, they are 3 different op-amps. Since they are 3 different op-amps, the noise spectral density will look the same, but the noise voltages are uncorrelated. Okay, so let's call this as Vn1, this as Vn2, and this guy as Vn3. So these 3 noise voltages are uncorrelated. Now what does it mean is that the noise voltage at the input of this guy is independent of the noise voltage at the input of this guy. Okay, so that's what uncorrelated means. The advantage of when I say uncorrelated, you can find the contributions of each noise source to the output, and then to find the overall spectral density you can just add up all the three noise spectral densities. Okay, you can in other words you can add their powers, because they are all white noise sources. You can add their power spectral densities too. I'm going to call S1 of F as the spectral density of noise spectral density of the first op amp, and S2 of F as the noise spectral density of the second op amp, and S3 of F as the noise spectral density of the third op amp. Now I want you to find out SO of F, SNO of F, the noise spectral density at the output and the noise spectral density at the input. So SNI of F due to these three op amps. To do that, first I need to find out the transfer function for each of these noise sources to the output. Once I know the transfer function of each of those noise sources, I can simply multiply to find out the output spectral density SNO of F. I just have to multiply the noise source, individual noise sources Si of F by the transfer function squared. Okay, mod of the transfer function squared. These results follow from random processes, theory of random processes. You can read up any textbook, but since you're already in your third year, I'm assuming you guys already know this because you have done a basic course on communication theory and also basic course on analog design. So the output referred noise is simply given by the individual noise sources multiplied by their magnitude of the transfer function square. So all I need to do is find out the individual transfer functions to the output and then multiply it by, and then I can add all the three in their power spectral densities. So first we'll assume only Vn1 is present. In fact, I don't even need to do that. I can assume both Vn1 and Vn2 are present as noise voltages. I can then the differential voltage at the input is simply given by Vn2 minus Vn1. That's the input differential voltage. This will see, if you refer it to the output, we'll see a gain of Vn2 minus Vn1 times G. That's the gain of this amplifier. Okay. This can be written as G times Vn2 minus G times, I'll write it as plus minus G times Vn1. Now to find the contribution due to the third op amp, I'll have to assume the first two contributions are 0. So I'll have to ground these two inputs. If you ground these two inputs, VO1 and VO2 comes to ground, right? It's just an amplifier with a 0 input. So these two will be at 0. If these two nodes are at ground, now the transfer function from Vn3 to the output, assuming the op amp doesn't draw any input current, will simply be 1 plus Rf by R4 by R3, which will be 2. So that VO due to Vn3 will be, I can maybe directly write this, you will have G times Vn2 plus minus G times Vn1. So minus G times Vn1. The Vn3, see, remember Vn3 appears at this input. So if you guys look at this guy here, you will have a non-inverting amplifier. So I'll draw this part just so that it's very clear. So you'll have a voltage source of value Vn3, and you will have two resistors which come in parallel of value R by 2, and the circuit reduces to something like this. Since no current flows at the input, the drop across this resistor R is 0, so I can just treat it as ground. So now this is a non-inverting amplifier with a gain of 2. So that's what I've written it as, 2 times Vn3. This is the overall output voltage. From this, I know the transfer function for each noise source. The transfer function for Vn2 is plus G, Vn1 is minus G, Vn3 is 2. So SNO of F, the noise spectral density at the output due to the three different noise sources, because I'm saying assuming all these three are of 0, noise is generally assumed to be of 0 mean, and noises of the three op amps are treated as uncorrelated. They are not related to each other. Sorry, they are not related to each other. Therefore, you can just add all their power spectral densities, okay, with appropriate scaling factors. The scaling factors here is the transfer function square. So it will be g square times s2 of f, or let me call sn2 of f, plus minus g the whole square is g square times sn1 of f, plus 4 times sn3 of f. This is the total output referred noise due to the 3 op amps. If I have to find the input referred noise, I will have to divide it by the factor g. So the ni of f is simply SNO of f divided by g square. Okay, if I have to refer it to the input, see, remember, this is noise spectral density. It's usually a power spectral density. Therefore, I am dividing it by g square. If I were to ask you the voltage spectral density, then you can divide it by g. But since I'm asking power, since we are finding power spectral density, units for this will be volt square per hertz. Okay, so that's why I've divided by g square. So this guy will be is given by Sn2 of f plus Sn1 of f plus 4 by g square times Sn3 of f. It is given that the noise floor of all the 3 op amps is 1 nanovolt per root hertz, or I can write it as 10 power minus 18 volt square per hertz. Okay, this is root hertz. I should have written it as, probably mentioned it as 1 nanovolt per root hertz. Yeah. So we are supposed to find the input referred noise spectral density. So since G is given to be 1000, 4 by 1000 square, it will attenuate it by a significantly large factor. Okay. So these two guys, since Sn of f is given by 10 power minus 18 volt square per hertz, they both are same. I can multiply it by a factor of 2, plus this will turn out to be 4 into 10 power minus 6 times 10 power minus 18 volt square per hertz. So if you see, right, this is 6 orders of magnitude lower. So I can ignore this term. Your noise spectral density will just be 2. So if I want to express it in volt per root hertz units, it will be root 2 or nanovolt per root hertz, or 1.4, approximately 1.414 nanovolt per root hertz. That's the input referred noise due to the 3 op amps. So clearly we can in fact extend the analysis and find out the noise due to the individual resistors. There are many resistors in the circuit. You can find out the noise due to the second stage resistors. All the second stage resistors will all be getting attenuated by, when you refer it at the input, it gets attenuated by the gain of the amplifier. Okay, the gain of the first stage, which will be a significantly large number. So yeah, that's the that noise of the second stage really doesn't matter much. The noise, even for the resistors, the first stage resistors will matter the most. Okay, in fact, the resistor RF will be of much larger magnitude, and therefore we will see that the noise RF will contribute significantly to the output noise. Even the noise of this resistor will also matter. Okay, you can't ignore the noise of this resistor. That will also matter. In fact, that will also see a huge gain. In fact, this noise, this resistor here, can also add significant noise. Okay, I'll probably in another lecture, when we talk specifically about noise, op amp and noise transfer functions for op amps, I'll talk in more detail. But right now I just wanted to take the noise of these 3 op amps. Since we already performed the analysis of offset voltages, I thought it's much easier to follow here. Okay, so the conclusion from the analysis, the first stage op amps will add most of the noise, and we can simply find the noise spectral density of each of the op amps. Okay, since both the op amps will be designed to be identical, at least when you are doing a circuit design of these 2 op amps, the noise spectral density will look the same. You just have to multiply it by a factor of 2. Okay, for power you will have to multiply it by a factor of 2. In nanovolt per root hertz units, it will be multiplied by a factor of root 2. So it increases. Okay, it increases by the same amount. In decibel units, we say that the noise spectral density, okay, increases by 3 decibels. So whenever you add two noise sources of same magnitude, the overall noise spectral density will increase by 3 decibels. This will be the units for this is usually dBV per hertz. It's just decibel units of spectral density. That's it. So it will increase by 3 dB or by a factor of 2 in noise spectral density. If you voltage units, it will be by a factor of square root 2. Okay, thank you.